Just take it easy. Take it easy. Just do the quiz first. Yeah, we got a first quiz, second quiz, and then the test.
How many units after this?
Just 2 units after this. So what we're going to look at today is area between two curves. We've already learned, let's say you have a parabola, that you could find the area from one point, let's say 1 to 4, you could find this area. Oh, we got to get our crayons out. Perfect. Let's use green. You could find this area. Now, if you had another function, just because we can, we'll make it an upside down quartic function. Why not? So you have another function that goes like this. And it just so happens that it intersected this at here and here. And if you wanted to find the area under that curve from 1 to 4, you could do that in purple. That would be this. And that would be using what we did before. Now, what we're going to look at today is how can we find the area between, this is fun pen, the two curves. Ooh. Does that make it? Oh, see, if I lift it up, there we go. Happy day. All right. So how can we find that area between the two? Does it make sense if you can find the area of the one, the bigger one with the purple crayon, and the area of the smaller one with the green crayon? All you're going to need to do to find the area between the two is subtract them. Now, that's shown right here. This is the bigger one, this is the smaller one, and we can subtract them. Now, because of what we know about our properties of integrals, we could do it that way, or when you're subtracting integrals, you could put those functions together and subtract them right away at first, and then figure it out. One thing that's really nice about the area between two curves is we might have some examples where you have one function like this and one function like that, and the area between them, just because we're having fun with our pens today, we're going to fill this one full of stars. The area between them, notice that some of that area is above the x-axis and some of it's below, and that caused us like issues before because some of that area was negative and some of it was positive. The nice thing about finding the area between the two curves is you're not going to have to worry about that. You just have to do the one function, subtract the other function. It doesn't matter if it's above or below the x-axis. The area is going to come out as the correct answer. You just have to make sure that you know which function is the one on the top and which is the one on the bottom, and that's where you're going to subtract. If you subtract them the other way, you're going to get your final answer to be a negative instead of a positive because you've subtracted them backwards. But it'll still be the right number. So here's our two curves to begin with. Can you see that they're both parabolas? Okay? And the first one, which I'm going to underline here in blue, that's a parabola that opens up. I'm not going to put any x-axes on here. I'm just going to draw a picture of a parabola opening up. And this one that I underline in green, that is a negative x squared. That's a parabola opening down. Now, that parabola opening down, that's not green. Let's try that again. Here we go. The parabola opening down might look like that, and then there would be no intersection point and no area between them, or if you wanted to count this, all the area in between it would be infinite. But if they do intersect, it would have to be that the green one was on top of the blue one. Does that make sense? And then if you're finding this area in between, this one, oh wow. Nice. If you're finding that area in between, then you would have to do the green one minus the blue one. Now, some key things you need to know to find this area, you need to know where do they intersect? Where are they the same? How do we find out where two graphs intersect each other? You could graph them on your graphing calculator, and then that would tell you, yes. And if you didn't have a calculator, or it was a non-calculator part, put them together, what do you mean? Well, you've got two equations here, right? And you want to find out where they're equal. You could use substitution, and you could say, well, instead of writing y there, I could just equate the two equations and say, if they're the same, the y coordinates would have to be the same. Does that make sense? And if the y coordinates are the same, then the x coordinates are the same. So if we put these equations together, now we just have to solve what would x be. So if I move everything over to one side, you got 2x squared, the 2x's will cancel out, minus 8, factor this, so we get that this happens when x is equal to -2 and when x is equal to 2. So if we want to find the area, we're going to have to take the area of the green one. I'm going to call the green one g of x and the blue one f of x, just temporarily, to write out what we need to do. So we need to do the integral from -2 to 2 of the green one, which is g of x, and then we need to subtract the integral from -2 to 2 of the blue one. That's going to be the idea to find that area in between. What we're going to do is we're just going to subtract g of x from f of x. So now I'll put the numbers in. G of x was -x squared plus 2x plus 10. And I'm going to subtract f of x, which was x squared plus 2x plus 2. And instead of integrating right away, it makes sense to simplify this as much as we can. So we're going to get -2x squared, 2x minus 2x is 0, 10 minus 2 plus 8 dx. In fact, that does make sense to put them together because you can see that there's a lot less integration that you have to do. And when you have to evaluate, there's a lot less evaluating that you're going to need to do. Because now when we take the integral here, plug in 2, plug in -2, 16 plus 16 will be 32. Negative 16 over 3 minus 16 over 3 will be minus 32 over 3. So you'll have 96 over 3 minus 32 over 3. Equals 64 over 3. So again, the idea isn't too bad. You have to take time to find out where did the two graphs intersect. You have to think about the two graphs and decide which is the graph that's going to be on the top and which is the graph that's going to be on the bottom, so that when we're subtracting them, we realized that we had to do g of x minus f of x. If you get that wrong, your answer in the end would have been negative 64 over 3, because you would have done the smaller area subtract the bigger area. If that's the case, instead of erasing everything and redoing it, you could go back and put absolute value bars and just make a little note. I used the wrong one, but so I just put absolute value bars so I didn't have to rewrite everything. Because then I would know that you knew what was happening. And also, we saw that simplifying the two when you subtract them makes your integral easier to work with. And you can figure it out that way as well. All right, here's one for you to try. Okay, check how you did here. So when solving them, get x equals 4 and x equals negative 1. Well, I drew the pictures here, and I knew that the parabola was going up. So this line, if we draw, and I know that this line has a positive slope, so it goes like this. If those two things intersect and you're finding the area between them, can you see that the line has to be on top? Because if they don't intersect, well, then there's nothing between them. But if they do intersect, based on the way those graphs are, the line would have to be the one on the top for when you're subtracting. So then once you found out that they intersect at x equals 4 and x equals 1, or negative 1, sorry, then we can take our two functions and subtract them and simplify. And you get the equation negative x squared plus 3x plus 4. Yes? You put the x squared first?
Yeah.
So then your answer will come out to be negative. Then you'd have to go back and put absolute value bars and make a little note that you...
If you do that, where do you put the absolute value bars? Like right at the start?
So the absolute value bars, because we want to find the area. So as soon as I put area equals, if you wrote it the wrong way, this is now a negative answer. So right here, you could put absolute value bars. And then you would have to continue that all the way through till you get to your final number that's negative in those absolute value bars. Put one more set of absolute value bars, and then write it as a positive answer. So I find it's always very helpful just to draw that little sketch off to the side. It doesn't have to be perfect. You know it's a parabola, you know it's a line. If they do intersect and you draw that sketch, you can see that the line has to be on the top. Oh yeah, I'll scroll down here. Is that okay if I go that far? So now you can find the integral, plug in your values. Work with those fractions, get your common denominator, and you get 125 over 6. All right, here I'll put it up so you can check how you did. Find the line's going to be on the top again. Finding the intersection points will be -2 and 2. Why do I write A equals here?
Yeah, and not down there.
Oh, I just got lazy, I guess. So I wrote it a couple times, but yeah, I guess I could have had equal signs going all the way along. Would have been nice too. So here we have a cubic graph, x cubed plus 2x squared, and a parabola. Now something about an x cubed graph, because it's a positive x cubed graph, you know that it's going to start down here. It might have something like this happen in between, because that's what could happen with the cubic graph. And it will end going up to the right. And because our parabola is a positive x squared, it could look like that. Now, depending on where this happens, you might have, well, I should draw my parabola just a little bit wider, because parabolas don't increase as much. There. What you could have is something like this happen, where there, at one point, the blue graph is above the green graph, and at another point, the green graph is above the blue graph. And so if this were the situation, we are going to have to try to find the area here and the area here, if we're asked to find the area bounded between those two curves. If this is the case, we're going to find the one area by itself first, and we're going to find the other area by itself, and then just add those two areas together. First of all, though, we need to find out whether or not these do intersect with each other. Okay? So, if we set them equal to each other, we would have x cubed plus 2x squared equal to x squared plus 2x. Now, as far as putting this together and solving this, we'd move everything over to one side to make it equal to 0. And since there's a common factor of x, we can take that out. So we got 3 points. They do intersect at 3 points, at x equals 0, at x equals -2, and x equals 1. Now, if I wanted to graph both of these functions a little bit more accurately to start with, what are some of the things I could do? Well, for this function, which was, I don't know if I've labeled yours f of x and g of x on your notes. Or do your notes still say y? Yeah. So if you want to just change the first one to f of x and the second one to g of x, that way we can color code them. I'm going to make f of x green, g of x blue. No, I have to do it the other way because I started f of x blue, g of x green. Now, with f of x being the cubic function, x cubed plus 2x squared, can you see that you could have factored an x squared out of there and had x squared times x plus 2? And I'm going to remind you of some of the things that you learned in grade 12 pre-calculus as shortcuts for graphing these without having to go through the whole calculus of finding out where it's increasing, decreasing, maximums, and minimums. One of the things you learned in grade 12 pre-calculus last year, that once this is factored, you know the x-intercepts. So we know that it has an x-intercept at 0 and an x-intercept at -2. And because it's an x cubed, it's going to be coming from down here and coming up. What's going to happen at x equals -2? That 0 has a multiplicity of 1. Remember that word? So that means that it goes straight through at that point. But when it hits 0, that x equals 0 here has a multiplicity of 2. And anytime you have an even multiplicity, it's going to bounce off of that point and go back up. So we actually got a pretty good idea what this graph looks like. We just don't know how high this little maximum is. And we could find that if we wanted to with calculus. For our parabola, which was g of x, g of x was equal to x squared plus 2x. You could factor that as well, 2x times x plus 2. So it also has those 2 points as x-intercepts, which we already knew that they intersected at those 2 points, but now we can see what this graph is doing. And we now know that this other point right here intersects at 1. I can go up a bit. So there's a more accurate graph showing what's happening. So we want to find the area between -2 and 0, and then we're going to want to find the area between 0 and 1. Now between -2 and 0, f of x is above g of x. But between 0 and 1, g of x is above f of x. So as far as writing this out, let's figure out the integral from -2. Our area is going to equal the integral from -2 to 0. And now we're going to take the x cubed plus 2x squared, and we are going to subtract the x squared plus 2x. And then we're going to add the integral from 0 to 1. And here we'll have x squared plus 2x. That's your green graph on top. Subtract x cubed plus x squared. Is it the second one 2x squared? Thank you. That would have messed up all of our math for a little while. So I'm just going to simplify from -2 to 0. We're going to have x cubed plus x squared minus 2x. And then from 0 to 1 is going to be -x cubed minus x squared plus 2x. You might notice that they're just a negative multiplied by a negative of each other. We're going to get x to the 4 over 4 plus x cubed over 3 minus x squared, or 2x squared over 2, just to follow the pattern. And on the other side, you're going to get exactly the same thing with the opposite sign. In the first one, can you see when you plug in 0, you're going to get 0 all the way through. Minus, when you plug in -2, you're going to get 16 over 4 minus 8 over 3 minus 4. plus, plug in 1, I'm going to get negative 1 over 4 minus 1 over 3 plus 1, plug in 0. You will get 0. Close that bracket again. Can you see that 16 over 4 is going to be 4? 4 minus 4 is going to be 0, so you're just going to get negative 8 over 3. First big set of brackets just simplifies to 8 over 3. And here, if we get a common denominator of 12, we'll have negative 3 over 12 minus 4 over 12 plus 12 over 12. So if we get a common denominator here of 12, we're going to get 32 over 12 plus 5 over 12. 37 over 12 as an answer. So it really wasn't that bad to solve without our calculator, because it wasn't that bad to graph and see where they intersect, and the intersection points were quite nice. But now we're going to look at this same question, solving it with our calculator. And what can we do if we had our calculator? So first of all, what we're going to do is we are going to graph each of these functions. So the first one was, I'm going to write x cubed. Was it x cubed plus 2x squared? And the other function was x squared plus 2x. So there's our cubic graph. And there's our parabola. And if we wanted to zoom in just to see this part right there, I'm going to go just from negative 3 up to 3. And same thing, negative 3 up to 3. And that'll just zoom in our graph a little bit more. So these were the two graphs that we were trying to find. Now, there isn't a nice application on this one to shade this in between and shade in between 0 and 1. We still have to do what we did in our equation here, where we subtracted the two functions. So in order to do that, I'm going to show you a little shortcut that's nice. Notice that you've got, so in the first part, the blue graph was above the red graph. So what I'm going to type into y3 is I just want to take this one, subtract this one, without having to rewrite them all. And I can do that. If you have a newer calculator, there's a shortcut that you can go alpha y equals, which gets you to your fractions. And if you scroll over to y var, it has your different equations listed there. So I can just go y1 minus y2. Oh, I forgot the minus. y1 minus y2, and type that in that way. Similarly, in equation 4, I'm going to type in y2 minus y1. So now I've got both of my functions listed. I've also got y2 minus y1 and y1 minus y2. If you have an older calculator, in order to get the y2 and the y1, you'll have to hit the vars button. This might be just as easy even if you have a newer calculator. And then go over to yvars, push enter on function, and they're all listed there. It's a little bit more complicated to find. But they're under the variables button, and then go to your functions. So now what I'd like you to do is go back to y equals, and if we hit graph right now, you can sort of see from my graph with all the colors there, there's going to be a lot of stuff going on. And you don't necessarily need to see that all. But you don't want to delete the functions that are in y1 and y2 because you need them. So what you can do is you can go over to the equals sign, which is black, and if you push enter, it unhighlights it, which means that equation is still there, it just won't graph it. So if I turn off all the graphs except for y3, which was y1 minus y2, and now I hit graph, it just shows what you get when you do y1 minus y2. And for y1 minus y2, we wanted to find this part right here. Right? That's this area. When you do y1 minus y2, that's finding that area. So if we go to our calculator, and we calculate number 7, the integral, from -2, lower limit -2, to an upper limit of 0, it'll shade that in, and that should equal 8/3. Okay? It comes up as a decimal, not as a fraction. The nice thing, anytime you calculate something on your calculator, the calculator now knows this is the last answer you found. So if we go out of this screen and go to here, if I just want to see what my last answer was, I can go to answer, so second answer, and push enter, and it still has 2.667 in there. Something that might be nice to see is hit your math button. Are you aware of the fraction thing on your math button? So that'll just change that answer to a fraction, and we can see, yes, it is exactly 8/3 like we found before. Now, if we want to find the area between 0 and 1, so I'm going to just go back to my y equals, and now I'm going to turn this one off and turn this one on. Because now this is the other graph, subtract the first graph, and now we can find, second, calculate the integral from 0 to 1. And that should equal 5/12. So if I go out of here and change that answer to a fraction, sure enough, it equals 5/12. Yes? So you get to shade it in by when you go in your graph. So here's my graph. Let's say I want to shade this part from -2 to 0. So I go second, calculate, and the 7th one is the integral. So number 7. And now I can go from -2 to 0, and now it will shade in that part. So one thing you might notice is, hey, that's the same answer that we got the first time through, but it's negative. So if you know that your answer is going to be negative when you subtract it the wrong way, you could get away with only doing one of these. Because this area is 8/3, but below now. Because all we did was flip the function over. So if you wanted to do only one with your calculator, you could do that as well. I think the new TI Inspire allows you to have both graphs and shade them both in between, but I don't think they have an app on these ones yet for that. Yeah. So that's how you would do it with a calculator. So I don't know if that's that much faster, because you might be slower on your calculator because you haven't used it as much, but it is easier. And if you wanted to get an answer just quickly because you were figuring something else out and you were like, oh, what is the area between those two curves? Then you could do that. Okay, so we are going to, since there is more than 10 minutes left, practice some questions.